Okay, I'm going to talk about how to remember what the spherical volume element is. And the volume element is dv equals rho squared sine phi d rho d phi d theta. And I think the rho squared is easy to understand, because now we see it has dimensions of meter cubed. And the reason these other terms do not contribute is they are dimensionless. They're measured in radians. Remember, if we have sine of 2 meters, that is meaningless, and it doesn't make sense. So the only thing that you can plug into a sine is an angle of radians. Okay, but the more mysterious thing is, why do we have the sine phi? Right? I mean, even in polar coordinates, we had r dr d theta. There was no sine phi. It was just, you had the usual meter squared terms and your usual angle that was dimensionless. But where does the sine phi come from? So I think the easiest way to remember this is by identifying sine phi with r. Sine phi times rho equals r if we go back to our RZ diagram. So if you take the sine, you get r equals rho sine phi, and z equals rho cosine phi. So I think it's more sensible for r to appear in dv than it is for z. Right? Because now you can think of it as polar, the polar dv times a d phi contribution. And this d phi contribution is really just rho d phi. And the polar is now r d, well, I'm going to do d rho d theta. And our r really is just it's just rho sine phi. So now we get rho squared sine phi d rho d phi d theta, which is what we want. Okay, so I would think of rho sine phi as the polar coordinate radius. And everything else as spherical corrections. And so let me just talk about where this comes from. I'm going to give just a heuristic derivation first. So the heuristic derivation is to think of 3 arc lengths. So there's going to be an s rho times an s phi times an s theta, and this will be the volume. So you start with your point in 3 space, and if you first add a d rho, that is your first arc length. Now, if we, let's just write this in the ZR plane first. So now if we change it by phi, then this arc length is rho d phi. Okay, so our arc length from the spherical change is rho d phi, and our arc length from the rho change is just d rho. Okay, now to get our third arc length, I'm going to go back to the xy plane, and well, now what I'm going to do is I'm going to change theta, and because in the xy plane this is r, this arc length is now r d theta. Okay, so that's our s theta. That's our arc length from moving theta. So we have r d theta. We have rho d phi. And we have d rho. So the product of all these things will now be our dv. So we get rho r d rho d phi d theta. And because we know that r equals rho sine phi, we get rho squared sine phi times d rho d phi d theta. That's exactly what the spherical volume is supposed to be. Okay? So the reason for you can just sum this up by saying the reason for sine phi is the theta arc length has r d theta, not rho d theta. Again, because r is the polar coordinate radius. And theta is the polar coordinate angle, or the azimuthal angle. It's not the polar angle, that's phi. But anyways, there's another a slightly more systematic way to get this. I think the heuristic way is just I think it's the quickest way to think about this. But if you're unsure if the heuristic works, or unsure of the motivation, I can tell you there's a quick, more mathematical way to do it. At least it's somewhat quicker than it could be. And I also I'm not a huge fan of how the book did theirs. So in an earlier video, I showed that the cylindrical coordinate volume, you can think of it as 3 partial derivatives. You just take all the partial derivatives and all the coordinates and you multiply them. And then you multiply, and then to make sure all the denominators cancel, you just multiply by differentials. Okay? So you just do the exact same thing in spherical coordinates. Okay? So I claim that dv is the partial derivative with respect to the radius times the partial derivative with respect to the angle times, let me just do the phi here, times the partial derivative with respect to theta. And then you just can't make sure all the denominators cancel. And so now you multiply by differentials. Okay? So that's what it should be. So now it's just a matter of computing this thing. So I will use the compact spherical coordinates thing that I mentioned in an earlier video, which is r. You can think of it as r cosine theta, sine theta, nested circles. So that's your first circle. It's the xy circle. And now if you add the rz circle, it's rho sine phi. I'm just going to quickly write the xy circle here, just in case you need a refresher. And so now you just substitute the second circle in. Okay, so now let's do partial derivatives. So if you take the partial derivative in rho, you just notice it's linear in rho, so you just divide by rho effectively. So it is sine phi cosine sine. I'm not going to write the thetas just for brevity because they'll just cancel out. So now if I take the length, notice that the cosine sine has length 1. So now it's just sine squared phi plus cosine squared phi. So that's just 1. So now we just need the other ones. So dr theta, or let me do phi first. That will be just the outside circle that will be affected. So you get rho cosine phi, and then times the same stuff, which I'll just omit because we already know it has length 1. So minus rho sine phi. So now if I take the length, then we just get rho squared cosine squared phi plus rho squared sine squared phi. That's just rho squared. So that means our second one is just rho. So now if we do this finally with respect to theta, now the outside circle does not do anything. So rho sine phi, and so now it's just the inside circle that changes. So it changes to minus sine theta cosine theta, and then finally our last term is just 0. So now if we take the length of this, all we need to do is just square the first coefficient, because again, sine squared plus cosine squared equals 1. Right? So now you see where this rho squared sine squared theta comes from. It comes from the fact that the last component is 0 and doesn't give you a cosine squared. So there's no cosine squared. I'm sorry, that's a phi. There was no cosine squared phi to add to this because there's no theta derivative. Okay? So now if you multiply all these things together, we get 1 times rho sine phi. And that's that coefficient, because now we just will multiply by d rho, d phi, d theta. This will finally give us dv. And that's exactly what we want. Okay, I hope this is helpful. For those of you who are looking ahead, this comes from Jacobians of transformations. We'll talk about this a little later, and it's really the fact that the determinant collapses to just the diagonal terms. All these other things are just zeros. Okay, so you don't need to know about that, but I'm just saying that there is a reason that we can do this simpler form, and you'll understand that soon. Okay, thanks for watching.